In this talk, I will discuss a Hubble parameter estimate. H0 is 73.37 plus or minus 0.54 kilometers per second per megaparsec from the late-time universe in the BAO. I'll start with a question posed by Gerard and Hooft. What's the choice of vacuum as a starting point to talk about the space-time of cosmology and infer that there must be a finite temperature that will give rise to a missing term in the FLRW equations, namely representing heat. I'll then continue with some analytic solutions and conclude with an estimate of H0. So normally we start with Minkowski spacetime, and in fact it represents the zero temperature limit for geodesic observers. This of course is changed in the sense that an observer at constant acceleration sees the same Minkowski spacetime quite differently as you would infer, say, from a hyperbolic trajectory. And if alpha is the acceleration, then this observer in its own frame of reference will infer a Rindler spacetime that includes at a finite distance psi, this invariant distance to the origin as seen in Minkowski spacetime, a Rindler horizon. Now this Rindler horizon is interesting because with respect to it you can define a entanglement entropy that in spherical geometry would be the Bekenstein entropy 2 pi times the Compton wave, the distance expressed by Compton wave difference phi, and it will have an associated temperature, namely defined by the Unruh temperature. And these two results are satisfying the relationship that TDS integrates out to mc squared. In other words, the gravitational field is, or the binding energy of your particle to the Rindler horizon is equivalent to a total heat Q, that is the integral from 0 to psi of TDS. So how does this play out in the Sitter space? In the Sitter space defined by a constant Hubble constant, you would have a temperature non-zero given by this expression due to Gibbons and Hawking of the Hubble parameter times the Planck's constant divided by 2 pi. And of course, as the Sitter solution, it also satisfies a closure density equal to 3h squared over 8 pi g. So if you combine these two expressions, you will appreciate that the energy density satisfies this scaling, that it scales with t squared. And you can see here the constant of proportionality. But what is interesting is that then the diagram that one would look at for energy density as a function of temperature would no longer be strictly the classical result of t to the fourth, but in fact at very low temperature it would reduce to t squared, because at low temperature t squared of course is dominant over t to the fourth. In fact, if you apply a fit to the data of an expression like bt to the power alpha, where b is some positive constant, plus sigma times t to the fourth, then the data, remarkably, pretty much select alpha is equal to 2. Our data fitting result gives alpha is 1.94 plus or minus 0.46. So that's essentially this the Sitter scaling that at low temperature you have rho goes as t squared, in contrast to rho goes as t to the fourth at high temperature. Now, of course, we don't live in the Sitter space because, after all, there was a Big Bang, and that completely destroys time translation invariance, at least on time scales as large as the Hubble time. And equivalently, the Hubble horizon basically voids the asymptotically flat Minkowski spacetime in the face of this finite Hubble radius given by c, the velocity of light, divided by the Hubble parameter. So if you are contemplating on doing some low energy quantum calculation, you would be invoking a propagator, say for a massive particle, e to the I phi, and ordinarily you would do this in Minkowski spacetime. You don't worry about infinity. In other words, you can take your phase reference to be some constant or even zero. But in the face of the Hubble horizon at a finite Hubble distance, you would now have to take care of how you define your phase reference. And it, of course, will derive from the Hubble horizon, which by itself is dynamic. So you have to do this covariantly at the very least. So you can contemplate replacing this reference phase by an equivalent volume integral over 2 lambda. If you do that, and then of course you would take lambda to be proportional to the Ricci scalar tensor over this background FLRW parameterized by Friedman's scale factor A, then if you work this out explicitly, you'll get lambda is some constant times 1 minus QH squared. Ordinarily G will be 1, but let's allow for a slight reduction in 1 by some gravitational self-gravity. That would then reduce effectively the total energy relevant to gravitation. So by this term, you would effectively be looking at adding heat to the FLRW equations, and remarkably that allows you to write down an analytic solution. It's a bit more complicated than the usual lambda CDM, but in fact it does include lambda CDM, as I'll just show here by way of example. So lambda CDM is recovered by simply putting G is equal to 0 and of course restoring the cosmological constant. So you just put lambda equal to lambda naught. And then this expression reduces to the canonical square root expression of a cubic polynomial, whereas in the intended finite temperature limit, so we completely remove lambda CDM and we restore G is equal to 1, you get the following expression shown here, which is fundamentally different, although it has the same large Z. Asymptotics, of course, it has a singularity at minus Z is minus 1, so in the distant future it will actually blow up. At any rate, what is interesting in late time cosmology is that Q naught, as we all know, in lambda CDM will give you essentially minus 1/2, whereas in this solution with heat, you will find that Q naught is 2 times the value that you expect in lambda CDM, so it should be roughly minus 1. Okay, so if we now switch to H naught tension between what Planck measures and what the local distance ladder presents. So in the following, I will use prime to indicate the Planck results and unprimed results of the latter. Then the ratio of the two for H naught will be 1 plus 8.6%. Of course, we also have a constraint on the age of the universe. That's not something we want to mess up, because there is already a constraint from the oldest stars in the globular clusters, even though they are not terribly precise. But you certainly don't want to make your universe to be much older or younger than those ages. So we have 2 constraints, and mathematically we can include those in the form of a normalization, since we have explicit integral representations, of course, for the age of the universe if you fix a background. And likewise, of course, the BAO angle we don't want to change, so we get 2 integral constraints. If we then apply those, we will find that upon imposing the Hubble tension of 8.6%, we get then our estimate at psi, where I here introduce a parameterization of this gravitational constant that is approximately equal to 1, but more generally 1 minus a small amount, which I here factorize over psi times the fine structure constant. So psi now is my free variable. Then I find that psi is 0.49 plus or minus 0.1. So it's basically approximately at least 1/2. Okay, another look at the same we can do in the QQ diagram, where capital Q is dq dz, a little q is the usual deceleration parameter. And if we do a fit to the data of late time cosmology, we get these kind of results, where we note that lambda CDM will always have a dq dz, so a capital Q essentially less or equal than 1, whereas the cosmology with heat will have a capital Q that's typically greater than 2. So there is a nice gap between the two. And then if you take as a referee a polynomial, so completely unmodeled fit, then it turns out the polynomial selects the cosmology with heat consistently, and in substantial departure from what is seen in lambda CDM. At the same time, though, as also can be seen from this diagram, the Q naught of the cosmology with heat is approximately -1, and this ties in well with this work recently by Camarena and Valerio, who get -1.08 plus or minus 29, 0.29. Okay, so to conclude, H naught is larger than expected in lambda CDM, which we attribute to heat. As an extra term in the FLRW equations. And if we impose the H of the universe and the BAO through two integral constraints, we actually can infer that psi must be 0.49 plus or minus 1. So obviously it's tempting to think that perhaps some theory, hopefully known in the future, might indicate that psi is 1/2. Then H naught will be 73.37 plus or minus 0.54. What is error or this uncertainty is here roughly the uncertainty in lambda CDM. So this result is interestingly consistent with what Rees recently presented, namely 73.30 plus or minus 1.04.